Hello, welcome to another lovely morning of Chem 100. I know you had a big weekend with the exam and everything. So today we'll wait another minute or so again, as usual, for everybody to show up, and then we're going to go through the exam and let me know in the chat or on Discord if you have specific questions or you want to see more of what I'm doing on the exam. So we'll do that, and then we'll get started with this week's work, which is chemical equations. This is a little bit of a lighter week. I don't think you're going to have too much trouble with the content and the homework for this week, but it kind of leads us into next week, which is going to be a little bit more work. So um, anyway, good morning, Daisy. Good morning, Monica. Good morning, Alyssa. Hey, Anne. Hey, Renette. All right. Hey, Maria. So as I said earlier, I'm going to go through the exam, our exam. Hey, Lene, the, and talk about some. I'll spend a little time on some of the ones that had the most mistakes that I saw. If now that the exam is over, you should have access to this exam again with all the answers, but I think it's still password protected. So I will take that password off today so that you can just go through it and use it for studying for the next exam. All right. So, pure substances, not a pure substance. Gasoline is not a pure substance. These were mostly okay. It is, in fact, a mixture. So, yeah, future exams are cumulative. Not necessarily on purpose, but everything that we do kind of leads to the next thing. So, like, we're going to do chemical equations and reactions this week, but you need to know how to write down or name compounds to be able to put them into a reaction. So, like, those kinds of skills will be cumulative throughout. Morning, Jennifer. Oops, did I miss one? No, that was good. Okay. So again, stop me if you want me to talk more about any of these. And for those of you who did the live exams, we can also go through that sometime if you want, but I will also send you the answer key for that when I send you your detailed scores. The ones mentioned that were marked incorrect. Oh, you mean for you personally um that you sent me things about? Yes. Yes, I will. Yes, I will correct those. There's a few people who seems like, well, we'll talk about that when we get to that particular problem. But yes. Okay, compounds rather than elements. Those are going to be ones that are made of more than one element. Most people got those. So CCl4 and H2O. Okay, this was actually a widely missed one. So let's take a look at that. Here's our periodic table. So I think this is just a terminology thing. The periods are the rows, all right, because we say that the properties are periodic. They keep cycling back. When you like, for instance, if we take carbon right up here, then we go on to the third row. By the time we get back to this carbon position, that's again 4 valence electrons. It's going to have similar bonding capabilities, things like that. So every time we get back to the same position, we have the same number of valence electrons, the same chemical properties. So that's a period. That's periodic properties. So the rows are periods, and the columns are groups. So period 5 is the fifth row. So 1, 2, 3, 4, 5 down here. And then, so right in here. And then group 3 is the third column, which is here. So that is indium, right where my finger is right there. This one, you just had to count them out. So since that's in the parentheses, there's 6 O's, and then there's an additional one there. So we've got to make sure to put 7 there. This probably would have had more wrong answers if 6 was one of the answers, because sometimes elements aren't all grouped together. And this one, actually, while we're looking at it, we can see why those elements weren't grouped all together. And that was because this is clearly a polyatomic ion type compound. So you've got some hydroxide over here, and then you've got nitrate. So those are meant to be grouped together, and then that's why the oxygens are in different places there. All right, physical and chemical changes. These mostly went okay. Physical changes, again, you've got phase changes like condensation, and then you've got just mechanical changes like tearing, grinding, slicing, cutting, things like that. And then the chemical changes where you have actual change of what's there. So paper burns and becomes other chemicals. Frying, any kind of cooking with heat is generally chemical in nature. Rusting, bleaching, stuff like that. Okay, got another one of those, this time with properties instead of a change. So physical properties, phase changes again, colors, smells, things that you can see, things you can sense. Chemical properties, how do they react with other things? So flammability, explosiveness, reactivity, chemical properties. 1 centimeter is 10 millimeters. We're going to do more with unit conversions next week, but we did talk about just the basics of millicenti and kilo, so you should know those. All right, so if we measured these with graduated cylinders, we measured these with beakers, we want to look at accuracy and precision. In this case, if the known value is 12.0 milliliters, the graduated cylinder is both most accurate, meaning its average is closest to 12, and also more precise, meaning there's less of a spread or a range in the measurements. All right, if this is a measurement, then the 3, the very last digit, is estimated as always. Nice job with these measurements generally. I know they were a little hard to see for some people, so I sent you some zoomed in versions of them. But the program should have recognized that the last digit is estimated. So if you didn't have 54.9 there, but you had 55.0, or you had 54.8 or something like that, you should still have gotten that right. So when you go through and check your exam, if you were pretty close to this and it got marked wrong, let me know, because they may not have had the tolerances set properly. The important thing is that you get the correct number of significant figures. I mean, you get the correct measurement too, but that last digit is estimated. So if you think it marked you wrong for that erroneously, let me know. All right, so yes, I can talk about the Celsius one, the thermometer. So let's look at the thermometer. So the thermometer here, we have gradations, if we zoom way in, of every 0.1 degree C. So this is going to be, I can't even see it on my screen here, so let me zoom this in. So that looks like 40. So we've got 41, 2, 3, 4, 5, and 6. So we're between 45 and 46 there. Let's see. No, between 46 and 47. Yeah. So then when we zoom in, we see the 0.1 degree gradation. So this is going to be 46, this is going to be 47. So we got 46.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, and 0.9. So it looks to me like it's just above the 0.8. So that means that that we've got the 46.8. Those are all known, and then we have to estimate one digit past that. So 46.8, I don't know, 1 maybe. That would be my estimate. So their estimate is 46.83. So we're pretty close. The important thing, again, you get those 4 significant figures. But I'm not sure exactly how close they wanted you to be to that. So if you said 46.81 or 46.84 or something, I think you should still get that right because that last digit is estimated. So check your answer on that and let me know if you think it was too close and you should have gotten it right. All right, and then this one's a little bit more theoretical. This one was really widely missed, even when the measurement ones weren't. So that's telling me that you can, when you see a concrete example, you can do it, but maybe you don't quite get it in theory, which is okay because mostly we're measuring actual real things. But let's talk about this one. If a graduated cylinder has markings every milliliter, what is the correct measurement? Well, if the markings are every milliliter, we always estimate one digit past what the markings tell us. So if the markings are every milliliter, then the estimated digit needs to be the tenths of milliliters, the next digit over. So it should be 21.2 milliliters. You don't have enough precision to get extra decimal places, and if you just have 21, then you don't have quite enough precision. All right, and the boiling point of water, that was in the objective, so you should know that that is 100 degrees C or 212 degrees F. And then to convert Celsius to Kelvin, you're going to add 273. So 100 plus 273 is 373. And so 1 and 3 are the boiling points of water. Another one there, we add 273 again and get to 300. A calcium atom. Now, we're not talking about a calcium ion. We're talking about the whole atom. What is the charge on just the nucleus? Is going to be 20 plus because there's 20 protons because the atomic number of calcium is 20. So you've got 20 protons. That's 20 positive charges. So a calcium atom will have 20 plus charge in its nucleus and then 20 electrons around to balance that charge. All right, here's a symbol for carbon 14. If an atom has 7 protons and it's neutral, it has to have 7 electrons because that's how it balances out. All right, isotopes of silver. So remember, we don't actually need the X because we can get the identity from the atomic number. So we can go back to the periodic table and see that silver is number 47 right there. And so everything with a 47 is an isotope of silver. So there are 3 different isotopes here. This one, and this one. If it loses an electron, becomes positive, that's a cation. Selenium makes a 2 minus charge, which we can find because it's in group 6A or 16, 2 away from the end, the right side of the periodic table. All right, in chlorine 37, we've got 17 protons, which we get from the periodic table because the atomic number of chlorine is 17. And then we need 20 neutrons to make the mass number of 37. Ammonium fluoride is 2 ions, ammonium and fluoride, that's an ionic compound. And then, okay, this one was also pretty widely missed, so let's take a look. This kind of goes into the whole naming thing because you have to be able to do this because these 3 categories have different or use different names. So if it's molecular, if it's or covalent, if it's all nonmetals, so you've got carbon tetrafluoride and nitrogen monoxide right there. And then between the 2 ionic compounds, remember some metals make one type of ion, meaning they only have one charge. So barium in column 2A, an alkaline earth metal, only makes 2 plus charges. Whereas cobalt, which is a transition metal in the middle, makes more than one charge, more than one possible charge. So in this case, we would call this one barium sulfate. We would call this one cobalt 2 chloride. All right, and then we're getting into some naming here. So barium and nitrogen, we've got barium plus 2 and nitrogen minus 3, nitride. So we have barium nitride right there. Potassium and oxygen, potassium's plus 1, oxide minus 2, so it's K2O. And then calcium hydroxide. So the reason this one was typed in, I wanted to make sure that you could format these things correctly. So in order to write this properly, you had to know that hydroxide was OH. And you also had to know that that's because it's a polyatomic ion, you need the parentheses and you need to make the 2 subscript. So some of you sent me some kind of screenshot saying like, didn't I get this right? And the answer is sort of. If you don't format the answer correctly, that can be ambiguous. It's actually an important part of writing chemical formulas. So for instance, if you write CaOH2 without the parentheses, what you're really saying is that compound has 1 oxygen atom and 2 hydrogens. So the subscript only applies to the H. It seems like not a big deal, but if you don't have those parentheses, you're actually talking about a different compound. Same thing if you don't use subscript for those amounts. If you just like write the 2 as a big number there, that can be confusing as well because we're going to use those full-size numbers this week when we balance chemical equations. And we also know that if you make superscript numbers, so you put the number up in the top right, then that's a charge. So that's a little bit different as well. Right? Between calcium and carbonate, calcium's +2, carbonate's -2. A couple of these may have been algorithmically generated, so you may have gotten a slightly different question than what I'm answering because there were some different possibilities. But if you have a question about yours specifically, just let me know. Again, calcium and phosphate. So you had to know calcium, you had to know phosphate. And then this one was a little tricky because it's not a specific ion that we talked about, hydrogen phosphate. It's not one from the list. So this is one of those questions that I really wanted to see, can you take these concepts a little bit farther? So for hydrogen phosphate, we're taking phosphate and then we're just adding hydrogen to it. So to get this right, you had to know that you had to know what phosphate is, which it was on the objectives. And then you had to know that hydrogen generally adds a +1, which we talked about. And so if you put those together, you've got +2 from the calcium, +1 from the hydrogen, and then -3 from the phosphate. So that ends up being an overall neutral compound. All right, so then for these, I don't know why there's a bunch of other accepted possibilities. Oh, I see, because they had to do it in every single order because it's separated by commas and it didn't actually know how to break those out. All right, so these are the correct answers. Nitrate, you had to know nitrate is -1, sulfate is -2, and phosphate is -3. So rubidium's going to be 1-to-1 with nitrate, 2-to-1 with sulfate, and 3-to-1 with phosphate because rubidium is +1. Strontium is +2. Whoop, sorry. So that makes them a little bit different. So 1-to-2 with nitrate, 1-to-1 with sulfate, and then 3-to-2 with phosphate because you've got the +2 and the -3. And then with indium, we actually help you out here and say that assume the charge is 3+ because it's in the aluminum column, but we didn't really talk about it specifically. So assuming it's 3+, this is how it would match up with those different ions. Lithium sulfate is incorrect because lithium is +1 and sulfate is -2, so you need Li2SO4 there. Iron makes more than one type of ion, so that makes it iron 3 iodide. So this is kind of helping you out here because you have to categorize it first and then name it. Lead, again, forms more than one type of ion. It's not in a row that only has one kind of ion, so we have to call that lead 4 chloride. Strontium, it only forms one type of ion, so strontium iodide. Barium, only one type of ion, barium oxide. And then PF5 is covalent, so that's going to be phosphorus pentafluoride. Anything in that particular row in the halogens there, group 7A or 17, contains 7 valence electrons, so bromine would be one of those. Silicon has 14 total electrons, so the electrons would go 2, 8, and 4, and then the 4 would be the valence electrons, and then these 10 electrons would be the core electrons. All right, and then some Lewis structures. So if if you had trouble drawing these with the system, but you think that what you drew was mostly right, again, I can see your answers, so I can see all the stuff that you put in there. So let me know if you think that what you drew is right, but marked you wrong. So again, you can check out these formulas and let me know how it went. All right, so this one in particular, this is the correct structure. However, I believe there is another way that you could have drawn this, that would have the system would mark it wrong because it's technically not um, it's not the right structure. It doesn't actually exist in real life. But following the rules of the octet rule and the other stuff that we talked about, um, it could actually be right. It does actually work. So even though it doesn't exist in real life, the reasons it doesn't exist in real life are beyond what we've talked about so far. So if you got this wrong, but it has the right number of electrons and all the atoms seem to fit the octet rule properly, let me know so I can see what you put in, because it may actually be, even though I'm not going to say it's right because it isn't, but you wouldn't necessarily have known that. So I'll still give you credit for it. All right, we've got a trigonal planar there, and then this molecule. So the way it's drawn right here, this is a Lewis structure. That looks very, like T-shaped or something like that. But we know that that's not actually how we find the groups. So we have to look at 4 electron groups, 1, 2, 3, 4, and then since one of those is a lone pair, that's trigonal pyramidal in shape. And electronegativity increases across the period and decreases down the group. Remember, fluorine is the most electronegative, so everything kind of goes toward there. And then finding a nonpolar bond, we can use the electronegativities, and we find that a CH bond is nonpolar among those 4. All right, so that was the exam. Again, let me know if you have questions. We can also talk about it in lab if it's seems too hard to discuss over the internet. I do want to make sure you get all your points as necessary. So if you find something that seems not right, definitely let me know. I am working on moving points over. You'll probably notice your mastering chemistry up to this point and the quizzes have been moved into Blackboard. Once everything gets there and I get caught up on the labs, then I will make a weighted total calculated grade column. And so you'll actually see what your overall grade is at this point when the categories are weighted appropriately as in the syllabus. Okay, let's move on to chemical reactions. So I left this page blank because I didn't. Uh-oh. Unplug myself there. Okay. I left this blank because I wanted to just kind of go through it and talk about it together with you. So we've done chemical reactions already. We've seen some things like that before, but I want to talk about really how we express that on paper. So a chemical reaction we know is a a chemical change. Sometimes we might think of this as a reorganization of atoms or of ions. There are lots of different types of chemical reactions, different ways that chemicals react, but we've kind of talked about that already. Chemical change is what that means. So when we express a chemical reaction on paper, question, how do we access our exam results? So right now, I'm not sure that you can. In mastering chemistry, if you go into your scores and your grades, you should be able to see that. But the I have to take the password off the exam for you to actually be able to go in and see the exam and see the answers. So I forgot to do that this morning, but I'll do that today. And then you can go in and see the answer key just like I saw it, or just like I showed you it. Okay, so the way that we express that on paper, a chemical reaction on paper, is called a chemical equation. Right? So a chemical equation is different from a chemical reaction. The reaction is the actual thing that happens, the physical thing. And the equation is what we write down on paper. So sometimes that's a little confusing because sometimes we refer to something on paper as a reaction, but it's really the equation that is describing the reaction. So a chemical equation, let's just take an example and then we'll look at the different pieces of it. So here is a chemical equation. This is an equation describing the combustion of hydrogen combining with oxygen to make water. Now you should notice a few things about this equation. So first, over on this side, we have what we call the reactants. Oops, not reactant. Reactants. Sometimes these are referred to as the starting materials. Sometimes if you start with one larger molecule and then you're treating it with a smaller molecule or something like that, sometimes the larger one is called the reactant or the starting material, and the smaller one is called a reagent. Like in the testing we did for the ions last week, we really cared about the ions, and the test reagent was the thing we added to it. So that's where that word comes from. And then whatever's over on this side of the reaction we call the product or the products. So we've got some reactants combining, and the arrow tells us that we're moving from the reactants to the products. Sometimes we'll see reactions that actually go both ways because the products can also go back and form the reactants. So the fact that we only draw this in this direction in this example tells us that we expect this reaction to really only go in one direction. Right. Other things that you can notice here, we have the states written here. So that tells us something about what's going on. Yeah, good question. Why isn't water liquid? Well, in this reaction, when you combine these two gases and give it a spark or something to ignite, then what you actually form is gaseous water, water vapor. You don't form liquid water. Now, depending on the temperature, that gas could condense and become liquid water, but in the actual reaction, it's the gases reacting to make another gas, water vapor. And that's often why the states are specified, because if we just saw H2O, we know that water exists in 3 different states commonly on Earth: solid, liquid, and gas. So we really don't necessarily know that if we're not told in the equation. There are 4 common states that we'll see. The 3 that you're most familiar with, so solid S, liquid L, and gas G. Then there's a 4th common one, which is aqueous, and that's labeled AQ, and that is for something that is dissolved in water. So if a compound is dissolved in water, you've got a solution, then its state will be labeled as AQ, aqueous solution. Okay, so there's something wrong with this equation as I've drawn it here. And the clue is this term, equation. So can anybody find what's wrong with this equation right here? Something is not working quite right. Yeah, exactly. We lose an oxygen. So there should be 2 O's, yeah. So on the left side, if we count up all the materials we've got two hydrogen atoms and two oxygen atoms combined in these compounds, and then we form one water molecule. So let's actually draw those Lewis structures. Hydrogen Lewis structure looks like this, just HH. Oxygen Lewis structure looks like this. It's got a double bond and a couple lone pairs. And then water's Lewis structure looks like this. Like that, right? So if we're combining these two and then forming this, what it looks like is that one of these oxygen atoms is simply disappearing. So the two hydrogens go with one of the oxygens, and the other oxygen just disappears. Now that can't happen because of something called the law of conservation of mass, which states that matter cannot be created or destroyed in a chemical reaction. Chemistry is all about reorganizing atoms. We can't just destroy matter. We can't just take an oxygen and make it no longer exist. All we can do is rearrange things. So, so this tells us that there's something wrong, that this is not actually correct, the correct equation here, because we can't lose an oxygen. So we have, if we don't know what we're doing, or we don't know how to do this, we could maybe think that there are a couple different possibilities. So one is, well, maybe we should just, instead of doing O2, we could just do O. And that doesn't work because we know oxygen is O2. Like, this is a physical phenomenon. You can take some hydrogen, which is H2, you can take some oxygen, which is O2, and you can combine them and make water, which is H2O. So we can't change the identities of any of these species, any of these elements or compounds. We know hydrogen is H2, we know oxygen is O2, we know water is H2O. So for example, we can't just add another oxygen here and say, oh, let's make this H2O2. Then it works, right? Why is that wrong? I'm just going to delete it because it's wrong. But anybody know why that's wrong? Does anybody know what H2O2 is? Hydrogen dioxide, good guess. Yeah, I mean that's what it sounds like it should be named, but it's actually called hydrogen peroxide, which you probably heard of. So hydrogen peroxide is not the same thing as water, right? You can't fill up your bottle with delicious hydrogen peroxide and drink it. Please don't. So it's clearly a very different compound. And so anytime we change a subscript, we're actually changing the identity of the compound. We're making something different, a different chemical. And that's not okay because, again, this is a physical phenomenon. We can do this reaction, we can measure, and we can see that we make water there. So we can't just say, well, it doesn't balance, so let's change the water to hydrogen peroxide. It doesn't work like that. And then additionally, we can't just add more oxygen on over here. Yeah, it is actually a different ion because it's not really an ion, but yes. So there's oxide ion, which we've talked about, and there's actually peroxide ion, which is O2 minus 2. So there is a different oxygen ion there. So we can't add another atom of oxygen because, again, physical phenomenon, you can do this reaction and you can measure that there is no extra oxygen. So let's get to the real answer here. The real answer is that these do not react in a 1-to-1 ratio. Can I explain why H2 and O2 turns into H2O? Yeah, it has to do with the stability of their bonds, and we'll get to this a little bit more in the second half of the chapter, but we're basically breaking these bonds and forming these bonds, and it turns out that on balance, these bonds are more stable than these bonds. And so breaking these and forming these ends up giving you an overall more stable situation, which is why water doesn't really react with much stuff. I mean, there are things it will react with, but water is pretty unreactive on its own. You can't burn water, for example, but you can burn hydrogen and oxygen. So generally, reactions are going to go to the more stable products. All right, so what we're really saying here, what we did wrong, is that we said this and this should react 1 to 1 to make one of these. So one molecule of this, one molecule of this makes one molecule of this. But that's not actually how it works. All we need to get this to balance is for them to react in a different ratio. So what's really happening here is 2 hydrogen molecules react with 1 oxygen molecule and make 2 water molecules. So now, if we think about that, we can see that we don't lose those, we don't lose any atoms anymore. Everything works out. We start with 4 hydrogens, we end with 4 hydrogens. We start with 2 oxygens, we end with 2 oxygens. And the way we express that in the equation is something called a coefficient, which is just a big number that goes out in front of the compound. So we're going to say we have 2 hydrogen molecules, 1 oxygen molecule, so there is a coefficient there. It is 1, but we don't show it when it's 1. And then we make a product which there are 2 molecules. So the correct chemical equation shows that the ratio is 2 of these reacts with 1 of these to make 2 of these. And now we have a balanced equation. That's called a balanced chemical equation. All right. So that would be something for a very small reaction like this that only has a couple atoms. You could maybe kind of look at it and go, okay, well, we need 2 of these, and that'll balance it out. But as reactions get a little bit more complicated, that doesn't quite work. It's just hard to do in your brain. So we have some procedures to help you through that. And so let's try this on the next page. This is balancing equations. So here's what I would do if I were presented with an equation like this. So the first thing I want to do, and this is for any equation that I look at, the first thing I want to do is what I call an atom inventory, which is just how many of each type of atom do we have on each side. So I look over on the reactant side and I see that I have 1 potassium, 1 chlorine, and 3 oxygens. And then I look over on the product side and I see that I have 1 potassium, 1 chlorine, and 2 oxygens. So this tells me that this is not balanced because I have more oxygen atoms on the left than I do on the right. So I now am going to add coefficients to try to bring these things into balance. And every time I add a coefficient, I'm going to change or correct my numbers here. Yeah, thanks. There's no labels here. There's no states here. So states are not necessary for a reaction to be balanced. They are a nice way to describe what's going on. We don't always know the states. In this example, it's just because we're focusing on the balancing part. I don't have the states in there, but it's nice if you can put them in there. I think this whole worksheet doesn't really have the states in there, just so we can focus on that. But it's not something that you can necessarily know. So if you're writing down potassium chlorate, potassium chloride, and oxygen, you don't necessarily know which one is in which state, but it's something that can be given. All right, so what I'm going to do here is I'm going to notice that the potassium's balanced, the chlorine's balanced, but the oxygens don't. Yeah, thanks for asking. So we need to balance our oxygens, and the way that we're going to balance them is just like what we've done when we deal with ions. We've got 3 oxygens here, 2 over there, so we have to find a common multiple. And the way that we do that is to have 2 of these and 3 of those. So this way we have 6 oxygens on this side and 6 oxygens on this side. But here's the really important part. We don't just change the oxygens, because when we add a coefficient, we change the quantities of all the atoms in that particular compound. So yes, on the right side, we only change the oxygens because that happens to be by itself in this example. But on the left side, we've now changed the K and the Cl as well. So now we have 2 Ks on this side and 2 Cls on this side. So even though we've balanced our oxygens, we've actually unbalanced our potassiums and chlorines, but that's okay, because now we can correct that. We've got 2 on this side, we've got 1 on this side. So if we add a 2 here, now we've got 2 on this side, of each also. And now you can see 2, 2, 2, 2, 6, 6. Those are all balanced properly, and this is a balanced chemical equation. Right? So there is some trial and error involved here. There's some going back and forth and like trying a number here and trying a number there and trying to see what works and what fits. That's part of how it goes. It doesn't. You can't just look at an equation and just write down the numbers and assume it's going to be fine. Some are simple like that, but many are not. So you have to kind of keep going back and forth and trying some different numbers. So we'll do one more together, and then I'll leave you to work on some of these other ones on your own. So again, this one's a little bit more complicated. So let's write down our inventory of all the atoms that we have on each side. And then remember, we're going to look at the entire side. So the reactant side is these, and the product side is here. And those are all going to go in their table together, even if the same atom is in multiple different compounds. So we've got, on the left side, 2 sodiums, 1 carbon, so far, 3 oxygens, 1 hydrogen, and 1 Cl. Then on the left side, we've got 1 sodium, 1 carbon. We've got 3 oxygens, 1, 2, 3, 2 hydrogens, and 1 Cl. So then you look at all these numbers and you think like, wow, where do I even start? What do I balance first? Should I just balance the first one that I wrote down? Should I go down here and look at the hydrogens instead? And the answer is it doesn't really matter. There's with one exception. Any atom that is in multiple different compounds on the same side, you want to save to last. So for example, in this case, that would be oxygen. There's oxygen here, there's oxygen here. Now in this case, it balances anyway, so we wouldn't start with that, but we really want to save those oxygens till last, because if we change one of them, we could kind of throw the whole thing off and we don't know what that ratio should be. So any of these other ones, sodium or hydrogen, we could start with and it should be fine. So let's start with hydrogen down here. We've got 1 over here and 2 over here. So to bring those in balance, we're going to need 2 of them. And that's going to change our hydrogen count on this side and also change our chlorine count on this side. So now maybe since we messed with the chlorine, maybe we want to stick with that one next. We go 2 on this side, 1 on this side, so I need to add more over there. And now I've not only changed the chlorine, but I've changed the sodium as well. So I want to make sure to correct that. And then, as you can see, everything is in balance. So actually, by changing that, I also fixed the sodium, and now this all works, and this is balanced. So that we would write this equation just like this, but instead of the blanks by the ones that have just 1, the coefficient is 1, we wouldn't write blanks there. But that is how you would balance that particular equation. All right, so before we end today, I want you to try it so that you have a chance to ask me if something doesn't work. Yeah, you don't have to fill in all the blanks. I mean, if it helps to think about it, you can add 1s here at the end, because that is 1 there. We don't want to forget that. But no, in a chemical, if we were to write this equation out, we would generally not write the 1s, and we would write Na2CO3, and I can actually give you the states on this just because I happen to know them, plus HCl. Oh, sorry, plus 2 HCl yields 2 sodium chloride plus water, liquid, plus carbon dioxide gas. Again, I put the states in here because I happen to know this reaction, but you would not necessarily be able to do that just looking at those compounds. But you should be able to find the numbers, the coefficients, and balance the equation. All right, so why don't you try, let's skip that one for now. Why don't you try this one? Let's try this one right here. So calcium hydroxide and hydrochloric acid, and then we make water and calcium chloride. Give that one a try. And then we'll go through it together and make sure that we match. All right, did you get it yet? Okay, if you're still working on this, go ahead and keep working. You can even pause the video if you want, or just follow along. But we're gonna do the exact same procedure. We'll first inventory our atoms and then work from there. So we've got 1 calcium, 2 oxygen, 2 hydrogen. Oh, sorry, that's wrong. 3 hydrogen. Gotta watch that. Remember, we have to use the whole side, so we have to take those 2 hydrogens and this one over here, and then 1 Cl. Over on this side, 1 calcium, 1 oxygen, 2 hydrogen, and 2 Cl. So we can see here that we are not balanced in oxygen, in hydrogen, or in chlorine. So we can start from any of those. Doesn't really matter here. Let's start with the I don't know. Do you have a favorite? It really doesn't matter in this one because they're all separate. Let's start with the chlorine because that's 2 to 1. That's easy. So 2 over here. Okay, so we got 1 vote for Cl, 1 vote for H. We can do it both ways, and I can show you that it works either way. So chlorine, 2 here, 1 here. So we're going to add 2 here, and that's going to change our chlorine count to 2, and it's also going to change our hydrogen count to 4. So now we can go look at the oxygen or the hydrogen. We got 4 on this side, 2 on this side. So that means we need to add a 2 here to make a total of 4 on this side. And that also changes our oxygen to 2. And I think that's all balanced now. Yeah, so everything works out. So it should be 1 to 2 to 2 to 1. Now, if we had started instead with hydrogen, let's just see what that would look like. We would see 3 hydrogens on this side, and 2 on this side. So actually, that is one that maybe we don't want to start with because it's going to be a little tricky. If we have, and the reason it's tricky is because we've got 2 different compounds with hydrogen on the same side. So if we want to balance 3 to 2, okay, we can't just increase this by 1. We have to increase this one by 2, and then that tells us we need 1 more hydrogen. So then we go back over to this side and we're like, well, I don't know which one I should increase to get that 1 more. In this case, it's simple enough that it would probably work out anyway because you'd see that you could put a 2 here. But the fact that there are 2 hydrogens on the same side kind of complicates things. So that may not be the best place to start. If we start with oxygen, though, since that doesn't have that problem, then once again we should have everything working out mostly okay because we can take our water here and we can make it 2, which gives us 2 oxygen and 4 hydrogen. And then we can go to our chlorines and make a 2 over here, which gives us 4 hydrogen and 2 chlorines. And then we're balanced. So you do want to save anything that is in multiple atoms on the same side till the end. All right, so that's basically how this works. There are some like little hints and different ways you can do things. I would say don't. Some of these make it more complicated than it needs to be. Like if you're balancing things as a group, like the H and the OH, sometimes that can be helpful, but sometimes it cannot. Using this method that we just talked about is always going to work. It's just going to take some trial and error. And if things seem like they're not working out, chances are that you did something wrong or that you have the wrong equation to start with. So this is something we're going to talk about on Thursday. If instead of being given the formulas, you're only given the names. So let's say instead of giving you this formula, I said, write the reaction between calcium hydroxide and hydrochloric acid. The products are water and calcium chloride. So I actually wrote that out like in sentence form. Then you would have to come up with those formulas for each of these. And if you were off, like if you wrote CaOH instead of CaOH2, or if you wrote CaCl instead of CaCl2, then it would not balance properly. So when we talk about things being cumulative, that's part of what we're talking about, that um, you have to be able to construct the compounds properly, or the equation that you're trying to balance isn't going to balance. So if things aren't working out and you're trying different things like that, chances are something's wrong. Something's wrong with your equation. So go ahead and practice this for the next couple days. We're going to do a bunch of reactions in lab, either Wednesday this week or next week. So you'll get to try those out and practice writing some different types of reactions there. And then on Thursday, we'll talk about some more complicated reactions, and then we'll get into energy and how we talk about the energetics of chemical reactions. So let me know if you have any questions, and I will see half of you on Wednesday. So thanks, everybody. Yeah, so for the pre-lab on Wednesday, there isn't like an auto-graded quiz on Blackboard. So you just have to either print it out and fill it in, or just answer it in on separate paper if you don't have access to a printer. Yep. Thanks.